the diagrams and identify the geometries from experiment 10 in our lab manual. I'll be starting on page 143, doing an example with C3H6 to start off with. So the first thing you always want to do is figure out your total number of valence shell electrons. So I'm just going to write over here total VE, standing for valence shell electrons. And we know that each carbon, which we have 3 of, we have 3 carbons, contributes 4 valence shell electrons for a total of 12. And we have 6 hydrogens, each contributing 1 for a total of 6. So overall we have 18 valence shell electrons that we can play with when we're drawing our Lewis structure. The next thing we need to do is kind of lay out all of the atoms that we have present. So we have 3 carbons and we have 6 hydrogens. So for right now we don't really know where everyone's going to go, so we're just kind of going to lay out these hydrogens and we'll kind of figure them out as we start drawing our molecule. We know that the next step for us is to attach everyone. So when we attach everyone, we're going to use up some of our electrons to do that. We know that all of these atoms have to be attached somehow to each other. So you may go, okay, I'm going to have 2 hydrogens on each carbon. When I did that, I used up 16 of my valence shell electrons. 2, 4, 6, 8, 10, 12, 14, 16. So 16, I still have 2 valence shell electrons left over, which means I would have, originally I would look at my terminal atoms, which in this case are all hydrogens, and we would add extra valence shell electrons there, but we know the hydrogens can only take 2 instead of 8 electrons, so then we have no choice but to put our extra 2 electrons on a carbon. Now, hopefully the little red flag in your head is going off and saying carbon definitely should not have a lone pair on it, and that we're going to have to do some rearranging. The next rule tells us that we should look at octets. When I look at all of my hydrogens, I see that those are satisfied. However, none of my carbons, or excuse me, one of my carbons is satisfied with 2, 4, 6, 8 valence shell electrons, but 2 of them are not, and one of them even has a lone pair. So we're going to have to do some rearranging here. The first thing I would say is let's take our lone pair and make a double bond between our 2 carbons here. When we do that, we see now that this hydrogen on the end is now satisfied. I count 2, 4, 6, 8 valence shell electrons for this carbon. However, this carbon now has 10 valence shell electrons. 2, 4, 6, 8, 10. So he is no longer satisfied. He has too many. And we look to our last, molecule, or last carbon, and we see that we still don't have a satisfied octet here. We only have 6 around this last carbon. So we're going to move one of these extra hydrogens over to this carbon. And when we do that, we get the correct Lewis structure, which looks something like this. 3 hydrogens around this terminal carbon, 1 hydrogen on our central carbon, and 2 hydrogens on this carbon here. So let's go through and double check that everyone is satisfied. Each of the hydrogens has 2 valence shell electrons, so we know that they're satisfied. We're going to go through and count each carbon. I count 2, 4, 6, 8 on this carbon, 2, 4, 6, 8 on this carbon, and 2, 4, 6, 8 on this carbon. So each of the carbons has a satisfied octet, and each of our hydrogens is satisfied with the 2 electrons that it has. So this is a good Lewis structure for our first molecule. Now we also have to determine the geometries. We have multiple central atoms here, so I'm going to call this carbon A, I'm going to call this carbon B, I'm going to call this carbon C, just so that we can figure out each of them. So we're going to have carbon A, carbon B, and carbon C. And we're going to figure out the electronic geometry and the molecular geometry for each of these. So we'll just make a little chart for ourselves right here. So when we're figuring out electronic geometries, we first want to go through and determine how many electronic groups are around each central atom. When we do that for carbon A, we count 1 electronic group here, a 2nd electronic group here, and a 3rd electronic group here. Now remember, even though we have a double bond here, but all 4 of these electrons are pointed in the same direction, so they count as 1 electronic group. So this only has 3 electronic groups, which would make it trigonal planar. Now, when we have no lone pairs, what we have for our electronic geometry will be the same for our molecular geometry. So our molecular geometry for carbon A will also be trigonal planar. Let's look at carbon B. Carbon B, again, has 1 electronic group here for the hydrogen. We have a double bond here, but all of this would count as a 2nd electronic group. And over here we have a 3rd electronic group. So again, we're trigonal planar in both the electronic and the molecular shapes. Lastly, we have carbon C. This one's a little different. We have 4 electronic groups around this central atom. 1, 2, 3, 4 electronic groups, which would make this tetrahedral. And because there are 4 molecular groups as well, it is tetrahedral in its molecular shape. Sorry, misspelled that, but close enough. Okay, so this was our first example from page 143. We're going to move on to another example. If you need to pause right here to look at this video, you can. We're going to move on to our next example, which is the next one on page 143, which is C2H4O. So I'm going to go through and clear our sheet. Magically, whoosh, it goes away, and we're working on C2H4O. So we got a little more going on here, so we're going to go through and first calculate our total number of valence shell electrons. So each carbon, we have 2 carbons. Each carbon contributes 4 for a total of 8. We have 4 hydrogens. Each of those has 1 for a total of 4. And oxygen, we have 1 of those for 6. So we have a total of 18 valence shell electrons again. So again, we need to go through and try and kind of come up with a general idea of what we think the central atoms will be. Hydrogens are always really good for terminal atoms, so are halogens, right? Our chlorines, our fluorines, our bromines, those all make really good terminal atoms and really terrible central atoms. We know things like carbons, oxygens, all can make multiple bonds, so those are good options for central atoms. And so we again will go through and kind of just put our hydrogens around, because we know we're going to have to add those in at some point too. So my first bet would be to go through and go, okay, I need to attach everyone to everyone else. So I'm going to put some bonds between my atoms, and when I did that, I had used up 2, 4, 6, 8, 10, 12 of my valence shell electrons, so I still have 6 to play with. My next rule says that I would fill up the octets around my terminal atoms. However, in this case, they're all hydrogens, so they're satisfied. So now I need to go fill up octets on my central atoms. So I know that oxygen needs 2 more there, so we used up 4 electrons there. So we still have 2 more to use. And if I look here, I see that this carbon only has 2, 4, 6 valence shell electrons, so he would need an extra one there. If I look at this carbon, I see he also only has 6 valence shell electrons, but I no longer, right, I just used those 2, I have no more valence shell electrons to add, so I can't add another set of lone pairs here. So I have to go through and rearrange this in a way that would make sense, where I'm going to satisfy all of my octets. So what I'm going to do is I'm going to take this lone pair and let them be shared between these 2 carbons. We know carbon likes to make 4 bonds and have no lone pairs, and this carbon doesn't even have an octet yet. So when we do that, we're going to have carbon double bound to a carbon. Let's draw on our hydrogens. We had a hydrogen down here, bound to an oxygen with 2 lone pairs. And I'll just put the hydrogen down here now, but same thing. Let's go through and look at what we've drawn so far. I have a carbon that now has 2, 4, 6, 8 electrons on it. That's good. This carbon has 2, 4, 6, 8 electrons on this. This oxygen has 2, 4, 6, 8 electrons on it. So now all of my atoms have satisfied their octets. We want to look at the general bonding motifs. We see that carbon has 4 bonds and no lone pairs here. This carbon has 4 bonds and no lone pairs here, and we know that oxygens like to have 2 bonds and 2 lone pairs, so we're doing pretty good. Let's double check our total number of valence shell electrons that we haven't drawn too many. I count 2, 4, 6, 8, 10, 12, 14, 16, 18. So overall, this looks like a very reasonable structure for C2H4O. Now we're going to go through and do the geometries again. So since we have multiple carbons, I'm going to call this carbon A and carbon B, just so that we can differentiate them. Carbon A, carbon B, and we have an oxygen in there too. So let's do that. So we have electronic geometries and we have molecular geometries. So for carbon A, I again have 1, 2, 3 electronic groups around this central carbon. Even though there's this double bond, we know that both of those sets of lone pairs are going in the same direction. So our electronic geometry for this would be trigonal planar. I'm just abbreviating trigonal for trig, but same difference there. Now, we have no lone pairs on this central carbon, so the number of molecular groups is the same as the number of electronic groups, so trigonal planar for molecular geometry as well. On to carbon B. Similar situation, just kind of oriented differently. We have 1, 2, 3 electronic groups. We also have 3 molecular groups. And lastly, we have our oxygen. In our oxygen, we see 1, 2, 3, 4 electronic groups. So we have 4 electronic groups around our oxygen, which would make this tetrahedral. And we have only 2 molecular groups. Remember, lone pairs, they take up space and push the molecules out of the way, but when we talk about a molecular shape, they don't actually contribute to the overall shape. So the shape around this central atom of the oxygen is actually bent. Also sometimes called V-shaped. Bent or V-shaped is correct for this one. So again, I'll let you pause here if you need to in terms of catching up and drawing, but we're going to be moving on to our next atom, which in this case would be, or excuse me, our next molecule, which in this case will be SO3. So we're going to clear our structure and we're going to move on to SO3. Now the first thing to remember here is this is SO3, the neutral molecule, not SO3 minus 2, okay? This minus, we'll see an example in a little bit of a minus 2 one. This will have a different structure than this. Your manual asks you to draw the neutral structure, not the charged polyatomic ion. So we will see an example of a polyatomic ion in a little bit, but for right now we're going to go with our neutral structure. So again, we first want to calculate our total number of valence shell electrons. We know sulfur contributes 6 valence shell electrons, and we have 3 oxygens that contribute 6 valence shell electrons as well, for a total of 18 here. So we end up with a grand total of 24 valence shell electrons that we have to play with. Now, our rules tell us it's a very, very likely scenario that when we have one of one type of atom and multiples of another, that whatever we have one of is a good bet that that will be our central atom. So I'm going to go ahead right now and draw my sulfur in the center, and I'm going to put my oxygens around it like that. Again, when we're drawing Lewis structures, we want to go with what do we most likely see? How do we normally see things, and kind of use that as our basis. There will always be exceptions and things like that. We do have an exception to our octet rule with our sulfur in this situation, but you want to go with what you normally see, and then when things don't work out, then go to, okay, what are some exceptions? What are some oddballs that I have seen before? So our next rule is we need to attach everyone to everyone else. So when I use that, I do 2, 4, I used up 6 of my valence shell electrons to do that. So I have 18 valence shell electrons left. So now my next rule says to fill up my octets on my outer or the terminal atoms. So I'm going to go through and do that right now. So each of these oxygens needs 6 more valence shell electrons. And when I do that, 2, 4, 6, 8, 10, 12, 14, 16, I've now used up 18 valence shell electrons, so I have no more electrons that I can add to this molecule. These are all I can utilize. Now, when I look at this, hopefully a couple things you're realizing. When I have oxygen that only has one bond and 3 lone pairs, we know that this is not really how oxygen likes to be bound. We know oxygen likes to be bound with 2 bonds and 2 lone pairs. So each of these oxygens as they're drawn now would have a -1 charge on it. So this would be SO3 with 3 minus charges on it. The other thing we need to think about is the fact that this sulfur does not have an octet yet, so we need to address that. So we know that when we need to kind of have more sharing going on, that we can take one of our sets of lone pairs and share it as a double bond. So when we go ahead and do that, we end up with this molecule. Now, if you left the molecule just like this, we would know that, okay, this sulfur is now satisfied with an octet. We see that this oxygen is satisfied with an octet and has 2 bonds and 2 lone pairs, so is neutral. And both of these oxygens have an octet. However, these would both have a -1 charge associated with them. This is actually the molecule SO3 2. Like we said, this is not something we're drawing. This is not what was asked of us. So this is not a completed molecule for what we are asked to draw. So we're going to move ahead and keep thinking of things that we have to do to finish this drawing. Well, we know we need to have our overall molecule be neutral. Now, this is where one of our exceptions to our octet rule comes in. Because sulfur has access to the d orbitals, it can actually have an expanded octet. So it can take on multiple electrons past 8. So what we end up with is a molecule that looks like this. So each of the oxygens makes a double bond to the sulfur. Each of the oxygens now has 2 bonds and 2 lone pairs, which means each of these oxygens now have an overall charge of 0. So now we have the molecule SO3 with a neutral charge. In this case, we're only going to talk about the central atom around our sulfur. And to do that, we're going to look at the electronic geometry and the molecular geometry. We see that electronically there are 3 electronic groups. Now again, remember double bonds, but each of these sets of double bonds are only pointing in one direction. So we have 1, 2, 3 sets of electronic groups, which would make this trigonal planar. And again, no lone pairs on here, so our molecular geometry is the same as trigonal planar. This one was a little tricky. We're going to look at an example where we do have some lone pairs in a moment, so we're going to move on to that one. Again, if you need to pause to look at any of this before we move on, you are free to do so. So we're going to go through, clear off this molecule. The next example we're going to do is HCN. So again, first thing you should always do is do the total number of valence shell electrons. Hydrogen contributes 1. Our carbon contributes 4, and our nitrogen contributes 5. Also, one of the things you might want to start thinking about when you're going through and drawing your Lewis structures is how do these atoms normally like to bond? In your lecture classes, you may have gone through and made a little diagram or a kind of cheat sheet chart, which I'll go through with you folks real quick, just in case you have never seen it before. So HCN and O. These are some of the most popular atoms that we do Lewis structures with. So we want to look at how do we normally see these? So we're going to look at it in terms of valence shell electrons, bonds, and lone pairs. So we know that hydrogen has 1 valence shell electron, we know that carbon has 4, we know nitrogen has 5, and we know that oxygen has 6. How do we normally see hydrogen? How many bonds does a hydrogen normally make? We know that hydrogen can only make 1 bond, and it has no lone pairs. We usually see hydrogen bound to something like this, right? Whatever this atom is, there's always just a single bond. If you're drawing hydrogen with a double bond, you've done something wrong. And we shouldn't really, for what we're going to be doing in this class, hydrogen with a lone pair also should look weird to you and not be something that you normally are seeing. Next, we're going to look at carbon. Carbon makes 4 bonds, and again, no lone pairs. for the purposes of our class, if you see a carbon with a lone pair, you've done something wrong. It needs to have no lone pairs and 4 bonds. Now, those 4 bonds can be done a whole bunch of different ways. It could be 4 single bonds. It could be a double bond and 2 single bonds. It could be 2 double bonds. It could be a triple bond and a single bond. But in all of these cases, do we see that it's still making 4 lines, 4 bonds of some sort are being made here. Now, again, there's a bunch of different ways we could kind of organize this, right, where we could see different types of these 4 bonds, but in all cases, always 4 bonds, and we're never going to see it with a lone pair. Again, for the purposes of our class, you're probably going to have to redraw your Lewis structure if you gave your carbon 5 bonds, right? This is bad. No 5 bonds and no lone pairs. Let's move on to nitrogen. Examples that we see with nitrogen. Nitrogen makes 3 bonds and likes to have 1 lone pair. So examples of this would be something like NH3, where we see our nitrogen with one lone pair and 3 bonds. Right? This would be an example of a nitrogen in a happy situation, right? This is how nitrogen normally likes to be bound. In our example with oxygen, oxygen likes to make 2 bonds and 2 lone pairs. So oxygen, our classic example where we always see oxygen, is in water. We see our 2 lone pairs and 2 bonds. But oxygen can also be bound where it's a double bond. That still counts as 2 bonds and 2 lone pairs, maybe with a hydrogen and carbons like that. This is also normally seen for our oxygen. Now, there are 2 scenarios that we will also see. We will see an N+ scenario and we'll see an O- scenario. We're going to go through what these look like as well real quick. So again, we know that nitrogen still has 5 valence shell electrons, the oxygen still has 6. An N+ arises in something like NH4+, right, the polyatomic ion. What we end up having here is a nitrogen in the center where there are 4 hydrogens around it. Now, this nitrogen made 4 bonds and has no lone pairs. And because that lone pair is now being shared with an extra hydrogen, right here, this is the lone pair down here where it was nice and satisfied. Now it's sharing that lone pair with another hydrogen, right? So it's sharing an extra electron. So one of its electrons is being shared by this hydrogen and no longer belongs to itself. So it's kind of like it's missing one of its electrons, so it becomes a positive. Same thing happens with an oxygen. We know oxygen likes to be 2 bonds, 2 lone pairs, but sometimes we'll see oxygen with 1 bond and 3 lone pairs. When we see this, let's say it's a carbon bound to an oxygen and it looks like this, 3 lone pairs and 1 bond. Again, we know oxygen likes to be 2 bonds and 2 lone pairs. Now it has 3 lone pairs. So what ended up happening is one of those bonds, both of the electrons are now as a lone pair. When this happens, it's got 1 extra electron than it really wants. It should be sharing one of these in a bond. And because of that, we give it a minus charge. So we will see some examples as we go through more of these Lewis structures where we'll see these kind of exceptions. Now, in no way will this be given to you as a resource. This is something that you might want to commit to memory for yourself. This might be a good thing to put on flashcards, but this is just kind of a resource for you guys in terms of how do we normally see things when we're drawing Lewis structures. It's a good resource in terms of learning how to draw your Lewis structures. So if you need to pause right here to go ahead and get this information, you can, but I'm actually going to clear some of this off so that we can start working on our Lewis structure of HCN. So give me a minute to clear my board. We can go back to our HCN. So when we look at our HCN, we figured out our total number of valence shell electrons that we have. We know that in this case we're going to have 10 valence shell electrons to work with. Okay, so I got most of my screen cleared there. So we have a total of 10 valence shell electrons that we can work with. In this case we have H, a C, and an N. Now we know carbons and nitrogens can make multiple bonds and that hydrogen can't. It can only make a single bond. So we're going to just kind of lay these out like this and we'll see where it takes us. Our first rule tells us to go ahead and make a bond between all of our atoms. And when we did that, we used up 4 of our valence shell electrons, so we have 6 valence shell electrons left over. Our next rule tells us to go around and fill the octets around our terminal atoms. So when I do that, the hydrogen is satisfied, and the nitrogen would still need 6 more electrons. So when we go ahead and do that, I used up 6 more of my electrons. I have no more electrons I can draw. So now I need to figure out how to satisfy everyone's octets, and let's think about that common bonding motifs that we just drew, that chart that we just drew. Those are what we call common bonding motifs or common bonding patterns for each of these. So we know that this carbon right now only has 4 valence shell electrons being shared. It needs 2 more. So we can take 2 of our lone pair sets and we can make multiple bonds here. And when we do that, we would end up with our HC, a triple bond between our nitrogen and carbon. And lastly, that lone pair would just come down to the nitrogen here. So let's go through and look. Our hydrogen is satisfied. The carbon has 2, 4, 6, 8 electrons around it. The nitrogen has 2, 4, 6, 8 electrons around it. And let's look at it in terms of the common bonding motifs. I see this carbon has 4 bonds. That's what carbon likes. 4 bonds and no lone pairs. This nitrogen has 3 bonds and 1 lone pair, which is also good for it. So this is a really good Lewis structure of our HCN atom. And then lastly, we're going to do the geometry, so the electronic geometry and the molecular geometry of our carbon, which is our central atom in this case. We only have 2 electronic groups around this carbon, which would make it linear for the electronic geometry, and it's also going to be linear in the molecular geometry. All right, so I'll pause there again. Like I said, those common bonding motifs that you saw on the that we kind of drew at the beginning of this, those are really, really helpful. I would encourage you to draw those as a like a flashcard situation is a really good way to do that. The last example we're going to do from experiment 10 is on page 146, and this would be the CO3 2 minus. And in this case, or minus 2, sorry. Let's be good. 2 minus. So we have the CO3 2 minus. So when we go to do our total number of valence shell electrons for this one, we have a carbon, which is going to contribute 4, and we have 3 oxygens. Each of those is 6 for a total of 18. But now we also have to deal with the charge. So we have a charge associated with this of 2 minus. Each electron we know is a -1 charge, so we're actually going to add 2 electrons to it for a total of 24 valence shell electrons that we can play with. Now, if this was a positive charge, we would actually subtract the number of electrons from the charge that we have here. So let's go through and start thinking about what we're going to do here. We know when we have one of one kind of atom and multiples of another, that's a really good starting place to say, okay, I'm going to have that one atom be my central atom, and the others are going to be the ones around it. So when I do that and I go ahead and I connect everyone together, 2, 4, 6 of my electrons have been eaten up. So I have 18 left to play with. I know I have to go around and make octets on all of my terminal atoms first. So 2, 4, 6, 8, 10, 12, 14. Sorry, 2, 4, 6, 8, 10, 12, 14, 16, 18. I'm getting ahead of myself. All right, so now I look at this and I've used up the 18, right? So now I have no more electrons can be added on here, so I can only work with what I have. I'm going to go through and notice that each of my oxygens right now are satisfied. They all have octets, but my carbon does not. My carbon only has 2, 4, 6 electrons around it. So I'm going to have to do something to get 8 electrons around my carbon. So I'm going to choose to use this lone pair to make a double bond. So when I do that, I end up with an oxygen that looks like this. 2 bonds, 2 lone pairs. Hey, that oxygen's probably pretty happy. And then I have 2 oxygens down here that have my 3 bonds, or excuse me, my 3 lone pairs and 3 lone pairs and 1 bond. Now, when we go through, again, think of that common bonding motif, those common bonding patterns we saw. We know oxygen likes to have 2 bonds and 2 lone pairs, so this oxygen is satisfied. The carbon is satisfied because it has 4 bonds. We look down here. Each of these oxygens, they have 8 valence shell electrons, so they're happy, but it's not how it normally likes to be bound. So each of these oxygens actually ends up with a -1 charge. So we have an overall -2 charge, which is what we see here. So when we draw this out, we actually put a bracket around it. Oops, let's make that a little prettier. A bracket around it, and we put the 2- right here. Okay, so when you have a polyatomic ion or a molecule with a charge, always make sure you draw the bracket around the final Lewis structure and put the overall charge. Because these charges, because everything's covalently bonded, the charges are actually kind of a burden that's shared beyond between all the atoms in the molecule. So it's an overall -2 charge when we draw it. Now, you may have drawn it where a lone pair or a double bond was here or here, and all of these would be correct. In fact, we call these resonance structures. So I'm going to go ahead and draw both of those resonance structures real quick so that you can see that if you drew it slightly differently, that you are still correct, because we can have our electrons kind of float around within our covalent molecule. So we got a 2- here, and then we'll draw our last one. Let's see, that would put the double bond over here, lone pairs around our oxygens. And we put our 2- charge again. So all 3 of these structures are equivalent to each other. You only, unless your instructor asks you to, you only need to draw one, because it is understood that all of these are actually equivalent to each other and would be the same thing. So lastly, we're going to look at our central atom and do the electronic geometry and the molecular geometry. And again, we see that we have a central atom, and it has 3 electronic groups around it, as well as 3 molecular groups around it. So this would be trigonal, planar, in both electronic and molecular geometries. Now, it's important to know as you're going through and doing experiment 10, there are a lot of resources available to you on the internet. Please do try drawing these out. It will be important, and it's really good practice for you. I'm hoping that this video will be a good resource to kind of help walk you through any of the questions you're having.